Sometimes students struggle with the concept of using proper interval notation to describe the domain of a function. And really, this is less an issue with the interval notation and more a question of how do I know what to include or not include in the domain. So if you're unfamiliar with the concept of interval notation, please check out the video I've made about that. That talks about when you use parentheses and when you use brackets. But now let's think about that in relation to the domain of a function. So what we'll do here is we'll look at some important examples or some key examples that outline the issues you might face when you're algebraically trying to find and describe the domain of a function. So our first example, we're going to look at a function that looks like this. F of x, let's let f of x just be the square root of, let's say, x minus 4. Now, if we think about this graphically, from a graphical perspective, we know from the concept of transformations of graphs that this is the graph of the square root of x, and we're going to shift it right by 4. So that shift right comes from this subtracting 4 in here. So remember that the graph of the square root of x goes through the points 0, 0, 1, 1, 4, 2, and maybe we'll throw 9, 3 in there, right? So each of these is of the form x square root of x. And when we shift those right by 4, we're going to change our x coordinates by 4, so we get this new set of points, 4, 0, 5, 1, 9, 2, and 9 plus 4 is 13. Oops, that should be 8, 2, not 9, 2, and 13, 3. So on a picture, it looks something like this. Here's 4, 0, 5, 1, 6, 7, 8, 2, and then 9, 10, 11, 12, 13, 3. Our graph looks like that. And we can see from the graph that the domain of this function, it starts here, right? The domain is the x values that have a graph above them. So it starts here and it goes out there. And so we might be able to tell from our graph that our domain starts at 4, it goes to infinity, and because there's a dot there, we're going to include 4. So from the graph, we can tell that our domain, this is our domain, I should label that so we're not confused by what that represents, is 4 to infinity. Now let's say we want to approach this without having to draw the picture. Well, we can look at this and we see we have a square root function. And we know we can only, for function evaluation, we can only evaluate the square root of 0 or positive numbers. Can't take the square root of a negative and get a real value out of it, so we can only take the square root of 0 or positive numbers. In other words, whatever we have underneath our square root, whatever is under here has to be greater than or equal to 0. So that gives us an inequality to solve to figure out the domain of this. The domain of f is all x so that x minus 4 is greater than or equal to 0. We include 0, right? This equals sign we've got here, the greater than or equal to sign, tells us we're including 0 because the square root of 0 is 0. It's perfectly well defined. We get a real number when we take the square root of 0. So that then gives us that x, if we add 4 to both sides, is greater than or equal to 4. And we know from what we know about interval notation that this equal sign here gives us a bracket, and we're going to go again from 4 to infinity. So the inclusion here came from the fact that what's underneath the square root could be bigger than 0, but it could also be equal to 0. Let's look at another typical example where students get challenged about how to find the domain of a function. Let's look at example 2. Let's look at a function g of x is equal to 1 over, let's do x minus 3 times x plus 2. Now, that's not easy to graph using transformations. We could use a graphing tool like Desmos or something like that to get a picture of it. But we don't really need to know the graph here. We just need to know something about real numbers. We know that we are not allowed, we can't divide by 0 and get a real number for g. So, in other words, we have to remove from the domain of g, we must remove any x values that make the denominator of g equal, that doesn't look like a g, equal to 0. So in other words, we're looking at when does x minus 3 times x plus 2 equal 0. And we can see that that is when x is either 3 or negative 2. When x is 3 or negative 2. Now, these are danger values, right? These are values we have to eliminate. So in other words, if we were to draw a picture of the domain of G, right, we can just draw it in one dimension, one axis here, because we know the domain is just x values, and we've got negative 2 over here and positive 3 here, right? So this is the domain of G on a number line. And we know that we have to throw out this value, negative 2, and this value, 3. But the domain is everything else. Those are the only two values that cause us a problem. So now we have to ask ourselves, how would I write this in interval notation? So we're going to think of it 3 ways. We're going to think of this section here, this blue section. Then we're going to look at this orange section. And then we're going to last look at this purple section. Those 3 sections together make up the domain of G. So that blue section, ignoring everything else, that blue section there starts at negative infinity. That's its lowest value. It goes up to negative 2. And we don't include negative 2 because we have that open circle, right? Negative 2 is the value that is not in the domain, so we definitely don't want to include that. This middle section starts at negative 2 and goes up to positive 3. And again, we don't include those. Don't include those 2 numbers so they get parentheses. And then our last section, hopefully you'll see that, starts at 3 and goes to infinity, neither of which gets included because we never include infinity. And we're excluding 3 because it makes our denominator 0, so that doesn't get included. And then the last thing we do to make this nice and tidy via set notation is we put union symbols between those to say that we're taking all 3 of them together. All of them are included in our answer. So this right here is set notation for the domain of x, and here's just a picture of it. All right, our last example, we're going to put these 2 things together and we're going to think about what this means. So let's look at a function. So this second function here, this is called a rational function because it's a ratio of 2 polynomials. This up here is a radical function because it involves a square root. But what happens when we have a function that has a radical in its denominator? So our third example, we're going to look at h of x is 1 over the square root of x plus 2. So this has two things going on. The first thing is our denominator can't be 0. And what's under this radical sign, what's in the square root, can't be negative. So previously when we had a square root, we said that what's under there had to be bigger than or equal to 0. But putting these two together leads us to see that we need x plus 2 to be bigger than 0. Okay, so we're not going to do x plus 2 is greater than or equal to 0 because it is in the denominator. Apologies if you can hear the sound of the dog panting behind me. Right, we're not going to use this equal sign because if it's in the denominator and we let it be equal to 0, then we're taking the square root of 0 and now we're dividing by 0, and that's bad. So we're going to just say x plus 2 must be bigger than 0. And then, of course, solving that gives us x is bigger than negative 2. We have a greater than sign with no equals attached to it because equals makes the bottom 0. And so we write that as negative 2 to infinity.